Hello everyone, and welcome to my channel. This is a channel for educational purposes, and we try to shed light on some great theories of everything and important all-encompassing theories that you may not have heard of, or at least you don't know about them. You don't know how they work. And today is our 396th video that we've done on Dewey B. Larson and his reciprocal system of theory. And Mr. Larson was an American engineer who lived out west in Portland in the 20th century. He died back in 1990. And around 1959, he put out his two fundamental postulates, which were two short sentences having to do with his theory of the universe, how the universe was constructed. And then he took those two postulates and he, through a process of deduction, he derived a theoretical universe, basically a, if this, then that. And so if my postulates were correct, this is what the universe would look like. And then he compared his theoretical universe with the empirical universe that the scientists had been measuring and compiling in their laboratories and through their telescopes and, in their atom smashers over the centuries. And Mr. Larson was able to really create a great deal of that universe simply through theory. And so that is convincing to me that he was on to something. Maybe not completely correct, but definitely worthy of some investigation. So we're kind of taking an investigation here. Now, Larson's two fundamental postulates are the start of all this, and I think we're just going to read those, or I guess I have them memorized at this point, but the first one is that the universe that we live in is composed entirely of one component, motion. Motion existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then the second postulate is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Now, Larson has gotten some pushback for that second postulate. The first postulate is where all the so-called meat and potatoes are. And, primarily he's talking about a universe made out of motion. The universe is not made out of matter. It's not made out of energy. It's not made out of force. It's made out of motion. In particular, what he calls a scalar motion. And that scalar motion, motion without a direction, really, without a specific direction, that motion is the contents of the universe. Everything is made out of motion. And motion is the relationship between time and space. Time and space are thereby reciprocals of one another. And all motion is a fraction, with time or space as the numerator and space or time as the denominator. Now, I'm not going to spend too much time explaining that because in this article, I think Larson tries to explain it himself. So we're going to try to let him speak here today a little bit more. The article that we're looking at is called The Physics of Motion. A revolutionary new theory explains the mysteries of the subatomic world by Dewey B. Larson. Okay, so it starts right here. Physical science stands today on a pinnacle of success, unprecedented elsewhere in the history of human thought. The workings of nature are currently under scientific scrutiny all the way from the smallest subatomic particle to the most gigantic galaxy. A host of important developments have emerged from this intensive study and investigation with dramatic effects on human life. The unique feature of the physical sciences that has made this remarkable record possible is no secret. These sciences alone, out of all of the many branches of thought, have agreed on an objective standard of validity, one that, in principle at least, is independent of human opinion or judgment. If a scientific assertion is in full agreement with the observed and measured facts, it is valid. If it is not inconsistent with those facts, it may be valid. If it disagrees with the facts, it is not valid. When expressed in this way, most persons will probably be inclined to believe that this criterion is accepted everywhere, but this is not true. It is not accepted anywhere outside of the physical sciences. In religion, for example, the situation is just the opposite. A religious doctrine, by definition, is superior to anything else. And from the religious standpoint, an observed fact that conflicts with such a doctrine is worthless. Most branches of thought do not openly defy the facts in this manner. They simply ignore them when they are inconvenient. In the field of economics, for example, the wide gap between the assumptions of the theorists and the observed facts is a perennial source of comment. Many economists recognize that the obvious shortcomings of their theories are chargeable to the absence of a criterion of validity. As expressed by Professor Douglas Haig, the great obstacle to applying scientific method in the social sciences is that we have not yet established an agreed standard for the disproof of an hypothesis. Of course, scientists are also human beings, and as such, they share the ordinary individual's inability to fully live up to the ideals that he accepts in principle. Like other human beings, scientists dislike having to change their ideas, particularly if they are ideas of long standing. It is not probable that many of them would deliberately reject a new idea or theory that they recognize as being correct. The traditions of the profession are too strong for that, but history shows that they will go to extreme lengths to avoid such a recognition. Acceptance of new discoveries is therefore a slow process, but the existence of an objective criterion of validity exerts a pressure in favor of correct ideas and against incorrect ones that cannot be resisted indefinitely. Inasmuch as the application of this criterion involves checking ideas, concepts, theories, and beliefs against the observed and measured facts, one of the most important contributions that can be made toward resolution of outstanding issues is to add to the supply of relevant facts. One area in which additional facts are sorely needed is at the base of the physical system. Strangely enough, the great achievements of science in unraveling the intricate details of physical processes have been accomplished without any clear understanding of the fundamentals. As seen in present-day physics, space and time the basic entities of the physical universe are, in the words of R.B. Lindsay, quote, primitive, undefined concepts, end quote. The entities and phenomena of the next level, matter, charge, radiation, gravitation, are not much better understood. Indeed, the general tendency is at present to regard the true nature of these items as not only unknown, but unknowable, and to brand questions about their character and origin as meaningless. As one physicist puts it, quote, the answer to these questions is simply that there is no answer. Not that there is no answer as a matter of fact, but that there is no answer as a matter of principle. And this means that the question should not have been asked in the first place. How dare you ask me a question? I'm above you. Okay, so that's the end of the quote there. I'm wondering why Larson didn't identify which physicist that was that said that. But anyway, back to the text. The inevitable result of such a policy is an accumulation of unsolved basic problems. In view of the long and painstaking study that was given to these problems by generations of competent scientists before the decision to give up the search for answers was reached, it is quite unlikely that answers will be forthcoming unless some further facts are uncovered. The recent discovery of a whole series of previously unrecognized facts bearing directly on the points at issue is therefore a significant event. These facts were uncovered in the course of a theoretical investigation whose origins were described in an article in the July-August 1981 issue of Frontiers of Science. Of course, facts cannot be derived from theories, something that is often overlooked in modern practice. But what a correct theory can do is to furnish the clues that make possible the discovery of new facts or recognition of the significance of facts previously known. As explained in the previous article, the new theory is based on the concept of a universe of motion, one in which the basic entities are units of motion rather than units of matter. These basic units, we find theoretically, are necessarily scalar. That is, each is simply a relation between a unit space magnitude and a unit time magnitude. Scalar motion thus plays a role of primary importance in such a universe. Okay, this section is called Galaxies, Balloons, and Scalar Motion. In present-day physics, however, scalar motion is regarded as unimportant. Motion is often defined in such a way as to exclude it. But it is recognized by practically everyone that the motion of the distant galaxies, as observed by the astronomers, is in some way different from ordinary motion. The movement of galaxies illustrates scalar motion. In the past few decades, these astronomers have made a number of remarkable discoveries, among which is the finding that most of the matter of the universe is gathered into galaxies, huge aggregates containing billions of stars, which are distributed somewhat uniformly from the large-scale viewpoint throughout the vast region of space within the range of the giant telescopes now in use. Most of these galaxies outward from our location or inward toward us can be measured by means of a change in the frequency of the light that we receive from them, an effect similar to the difference in the pitch of the sound that we receive from a train whistle. depending on whether the train is approaching or receding. From this change in frequency, the Doppler shift, as it is called, the astronomers have found that distant galaxies are all receding from us at extremely high speeds that are proportional to their distances. The analogy that they almost invariably use to assist in explaining their findings is that of an expanding balloon. Almost any astronomy textbook contains a statement such as the following, taken from one of them. Quote, "The common analogy likens the galaxies to spots on the surface of a balloon that is being inflated. As the rubber stretches, all the spots move away from each other." End quote. A still closer analogy would be an expanding plastic ball or other three-dimensional object with identifiable entities scattered throughout its volume. In any event, the widespread use of such an analogy in explaining the galactic motion demonstrates that just about everyone realizes that the motion with which we are dealing in these examples is not the ordinary type of motion that is so familiar to us. Notwithstanding this general recognition of its unique character, the expanding balloon type of motion is completely ignored by the physicists. Apparently, the theorists have not regarded it as being of sufficient importance to warrant critical examination. The physics of expanding balloons has not been an inviting field of study, but new light has been thrown on the subject in the course of the development of the theory of a universe of motion. This has prompted a full-scale investigation of the scalar motion phenomena. The motion of our ordinary experience is vectorial. It has both magnitude and direction, and can be represented by a vector. In order to define a direction, it is necessary to relate the motion to a reference system. The reference system used for most purposes is a three-dimensional system of spatial coordinates, stationary with respect to some selected physical feature, such as the surface of the Earth. Vectorial motion may thus be described as motion relative to the other objects in the particular scalar system, and has no inherent relation to any spatial reference system. In the scalar system of galaxies, for example, each galaxy is simply moving outward from all others. This motion has a magnitude positive because it is outward, and results in an increase in separation, but it has no direction. Such a motion is, by definition, scalar. Although it has no inherent direction in the context of a spatial reference system, a scalar motion can acquire such a direction by means of a physical connection to the reference system. For instance, an expanding balloon can be placed on the floor of a room. The system of galaxies cannot be placed in anything. But the same result can be accomplished by introducing reference axes into the system. The effect of a physical coupling of the expanding balloon to a reference system is to give one spot on the surface of the balloon a specific location in the reference system, and to assign directions to the motions of each of the other spots. As can easily be seen, this direction is a property of the coupling to the reference system, not of the scalar motion. If the coupling is altered by moving the balloon, the motion itself is not changed in any way. All spots continue moving away from all other spots at a constant speed, just as they did before the change. But the directions of all motions are altered. The section is called What is Scalar Motion? Insofar as they apply to motions of the expanding balloon type, the foregoing points are generally recognized. But as little attention has been paid to them, the properties of scalar motion have not heretofore been examined critically. The long overdue analysis initiated by the theoretical study mentioned above reveals that because of the causal nature of the consideration previously given to scalar motion, a very important point has been overlooked. This has left out not merely one, but a whole assortment of blind spots in the field of view of modern science. As already noted, it is recognized that the coupling of a scalar motion to the reference system can be altered without change in the motion itself. It is further recognized that because of this freedom to change the nature of the coupling, the motion of any particular moving object in a scalar system can take any direction. What has not heretofore been recognized is that this ability to take any direction is not limited to a constant direction. Systematic study of motion was begun in the days of the ancient Greeks, but it was not until 2,000 years later that Galileo found the key to a real understanding of the subject. This crucial advance was the discovery that an object in motion continues in motion indefinitely unless acted upon by a force. In other words, continuous and uniform motion is permanent. Subsequent investigations have extended this finding to directions. Continuous and uniform change of direction, such as that which occurs in rotation, is also permanent. But because of the failure to make any systematic study of scalar motion and the consequent lack of appreciation of the fact that the coupling of a scalar motion to the reference system is independent of the motion itself, it had not been recognized that the direction of this kind of motion can be changed continuously and uniformly by rotating the coupling. A scalar motion with this kind of a changing direction is also permanent. The rotating change of direction can be illustrated by referring again to the expanding balloon. Obviously, the balloon can be turned around the vertical axis, passing through the spot that is resting on the floor. The inherent scalar motion of any other spot y on the balloon is not changed, but the direction of the outward motion of y, as seen in the reference system, is now distributed over the entire plane of rotation. A further rotation around a second axis distributes the motion in all directions. As can easily be seen by examination of the balloon situation, the characteristics of this distributed scalar motion are altogether different from those of ordinary vectorial motion. In vectorial motion, the magnitude and direction of the motion are interrelated. For instance, a motion in the direction AB superimposed on a motion AB prime of equal magnitude but opposite direction adds up to zero motion. But point Y on the balloon surface continues moving outward from all other spots, including the spot that is resting on the floor, regardless of the changes in direction. The scalar magnitude of the motion, the total outward motion of Y, is not altered by the directional distribution. The discovery of distributed scalar motion has a significance for scalar motion theory comparable to that which the findings of Galileo and Newton had for the theory of vectorial motion. In a sense, it is even more significant. Vectorial motion was already well known to both scientists and laymen, so that the task of these pioneers of modern science was merely to determine its properties and to systematize the relations between them. In the scalar situation, even the existence of distributed scalar motion was unknown, and the task of the investigator involved identifying this previously unrecognized type of motion, as well as deriving an explanation of its properties. And the task of the investigator involved identifying this previously unrecognized type of motion, as well as deriving an explanation of its properties. In the rotating balloon example, we are examining a distributed scalar motion of little importance, originated and maintained by human action. Once the existence of motion of this type is recognized, however, it is obvious that similar motion of natural origin can also exist. Whether it necessarily follows that such a motion does exist is a debatable issue. Some scientists and philosophers assert this as a principle of nature, as expressed by K.W. Ford, quote, "One of the elementary rules of nature is that in the absence of a law prohibiting an event or phenomenon, it is bound to occur with some degree of probability. To put it simply and crudely, anything that can happen does happen." Whether or not this is a rule of nature that has no exception, experience indicates that it holds good in general. We can be practically certain that naturally occurring distributed scalar motion exists somewhere in the basic areas of the universe. Present-day physical science recognizes no such motions, but as we have seen, there are a number of physical phenomena whose nature conventional science is unable to explain. When there is something missing that we have good reason to believe actually exists, and in the same general area there is something extra whose existence is not accounted for, an obvious possibility is that these are two manifestations of the same thing. Let us therefore look at one of these unexplained phenomena, the electric charge. Okay, I think we're going to stop right there and get into his next section tomorrow, which is called The Mystery of Electric Charge. And I think the key thing here that kind of adds to what I've been talking about over time is the concept of a distributed scalar motion, and that basically is a scalar motion in rotation, and that its effects are distributed over the surface of the sphere, or at least in one dimension of it. And he uses that as a key concept. Sometimes I forget about that concept that he uses, the distributed scalar motion. And so we will delve into how that works with the electric charge tomorrow. And meanwhile, thanks for tuning in today. Have a wonderful day.